Good morning.
Good morning.
Morning, ma'am.
Yesterday we looked how we can construct the confidence intervals. In 3 cases we learned. One is constructing confidence interval for the population mean. There are 2 different situations we learned. One is when the population standard deviation is known, then we have to use Z as a critical value. And when the population standard deviation is unknown, then we have to use T as a critical value, and the population standard deviation is replaced by the sample standard deviation. Then we move to the population proportion. If there is a large enough sample size, then the confidence interval, to construct the confidence interval, we have to use Z as a critical value to construct the population proportion confidence interval, right? So now, if we want to construct a confidence intervals for the either for the population mean or for the population proportion, right? Then how much of sample size we have to have? This is the section now we are going to study. So here, based on this, what is the sample size we need to decide the required sample size? We have to look at the margin of error, right? We have to look at the margin of error that is denoted by E. This margin of error is related to the level of confidence that is denoted by 1 minus alpha. So before deciding, constructing our confidence interval, we have to decide how much of units we are going to allow as margins and what is the level of confidence we are going to use. Based on these 2 facts, then we have to decide the sample size, and then we can construct our confidence interval. What is the meaning of this margin of error? This margin of error is called the sampling error, because almost the changes of these confidence intervals are because of the samples. When we are having a different samples, then we will get the different answers. So the variability we have to allow to accommodate the differences occurred in the samples, right? So that error is, so there is errors we can occur due to our samples. So this sampling error is called a margin of error. So the margin of error, simply we can say that it measures the inaccuracy in the estimate of the population parameter. What is the amount of inaccuracy occurred in the estimation of the population parameter? That is called sampling error. So now here we are allowing up to this one, now here this is our 1 minus alpha % of confidence interval. Then this is our confidence interval lower limit and the upper limit. The highest value, if it falls beyond this point, whatever point we are getting beyond this point, then the parameter will be outside of the confidence interval. Or here also beyond this side also, the parameter will be outside of the confidence interval. So we are alpha %, we are allowing for the wrong results, and 1 minus alpha %, this our true value will be included in this interval at the 95% confidence, right? So this length is called the margin of error. This length, this amount and this amount is called the margin of error. So the margin of error, according to this diagram, amount added and subtracted to the point estimate to form the confidence interval. So how we are saying that, how much of amount, this is our mu value, this is our expected mu value, From this, we are adding value from that. Suppose this is our one of the x bar is here, then x bar to plus we can allow, and x bar to minus we can allow. Right? So the amount added and subtracted to the point estimate to form the confidence interval. So now here you are saying that this is point estimate. So how much of amount we are adding and subtracting? Critical value into standard error. Right? This length is given by critical value into standard error. This critical value into standard error is called the margin of error. Right? So the margin of error is adding and subtracting to the point estimate to form the confidence interval. Right? So point estimate plus critical value into standard error is this maximum limit, and the point estimate minus critical value in the standard error is this minimum point. So we are allowing this point estimate will change by this amount. We are allowing our point estimate by change this this amount. So this amount is measures the precision of the, to what this extent we are allowing estimate as the true estimate to reflect the population, right? So critical value into standard error is the called the margin of error, right? So now we are determining the sample size for the mean. Here, this formula is applicable when sigma is known. The confidence interval x bar point estimate plus or minus critical value into standard error. So z into sigma over square root of n is the margin of error. This error we are allowing because of the samples. Because sample to sample, this x bar will be changed. So to what extent the x bar we can allow to change the x bar as a true estimate for the population mean plus or minus this amount, right? So here this measures the variability occurred in x bar due to the samples. Variability occurred in the x bar due to the sample. This is denoted by E, that is error, margin of error. So this up to this from the mean, up to minus from this mean, that over sigma over square root of n, right? So when sigma is known, right? So now we have to solve this one. From this we can get the n value, right? Because this margin of error is depending on the n value. By solving this one, we can get the n value. So how we are going to solve it? Now here you look at n, that is depending on the square root sign. The n value is depending on the square root sign. So now we have to remove this square root sign. So how we can remove? If we square this one, then this square root sign will be removed. So for the equation, what is the manipulation we are doing? As it's in the first semester we learned, what is the manipulation we are doing? Both sides we have to do, right? Without affecting our original equation. So now we have to remove this radical sign, that is square root sign. So to remove this square root sign, we have to squaring both sides, right? So that is to remove your square root sign, we are squaring both sides. E squared z sigma square root of n both sides. Then E squared is equal to z squared sigma squared over n. Now we want n. So we have to take n as a subject of this equation, right? So by doing the cross multiplication, n E squared is equal to z squared into sigma squared. So N is equal to Z squared sigma squared divided by E squared. This is the formula, right? So Z based on the level of confidence, we can decide the Z value from the standard normal table. Then sigma squared is the standard deviation norm we can get from the problem. Then E also we have to decide to what extent we are allowing, right? How much of amount we can, if suppose our X bar is, we can allow 2 units, right? From the sample mean. Then margin of error E is equal to 2, right? We are allowing the margin of error to change our mean values by 3 units or by 0.5 units. Then margin of error will be 0.5. That also, as a researcher, we have to decide how much amount we can allow to change our mean values by what amount. But in your problem, then you can get the clue how much of this is changed, allowing to change the mean value, right? To accommodate the variability occurred by the sample to sample, right? So this is the formula to determine the sample size for estimating the population mean mu, right? When sigma is known. So to determine the required sample size for the mean, you must know the desired level of confidence, 1 minus alpha. So from this, we can determine the critical value Z using the table. Then the acceptable sampling error, that also we have to know that. Then the standard deviation, that is population standard deviation. If we know these 3 facts, then we can find out the sample size. Then after deciding that sample size, then we can go for estimating the population mean. And that sample size we have to take and the related information we have to collect, and then we can estimate our mean value. So now, very simple example. If sigma is equal to 45, right? Population standard deviation is 45. What sample size is needed to estimate the mean within plus or minus 5, right? With 90% confidence. Now, what are we need the 1 minus alpha. So from this, 1 minus alpha is 90%. That is 0.9. And we need the margin of error, E. They said that we have to estimate the mean. This estimated mean will be allowed plus or minus 5. So the margin of error is 5. And also we need sigma, that is equal to 45. Right? So now straight away we have the value for E and we have the value for sigma. Now we have to decide Z. Right? So Z is our critical value. 0.9%, right? So now alpha, from that one, alpha is 0.1. Then alpha by 2 is 0.05. So when we are looking at our sampling distribution, X bar or Z, we look at Z, right? Now this is 0.5, 0.05. Now this value we have to get. Z by, this is our Z alpha by 2 value. Right? So if it is 0.05, then the half of this is 0, then half of this area is 0.45. Right? So now we can say that probability of 0 less than Z alpha by 2 is equal to 0.45. Right? So from the table, which row and column intersected, that should be 0.45 or approximately 0.45. Then you can get the Z value. That is almost, it is says 1.645. That is 1.65 actually, right? I think in a Z table, you can take probability of 0 less than Z less than 1.65 or 1.64 is approximately 0.45. So from this, your Z alpha by 2 value is 1.65. Right? So that is 1.65 holding square. Then sigma is 45 square, and E is 0.5. That is 219.19. Always we have to round up to the next integer, right? Because it's a sample size. So round up to the next integer, that is 220. Don't give it as a 290 because we need 219.19. So it is better to round up to the next integer, that is 220. So the required sample size is 220. Right? So only this is the formula. These are the things we need to decide the sample size when the margin of error, standard deviation, and the level of confidence is known. Right? If sigma is unknown, right, then how we can estimate, then how we can find out the required sample size. So when the population standard deviation is unknown, this can be estimated using the sigma have to be estimated when using the required sample size. But usually if sigma is unknown, our confidence interval is calculated by this. Now this is our margin of error, E. Right? So here also E is equal to Tn minus 1 into S over square root of n. So to remove, we have to find the radical n. So to remove this square root sign, we are squaring both sides. So E squared is equal to Tn minus 1 squared into S squared over n. Then from this, n is equal to, by doing the cross multiplication and divide by E squared both sides, then n is equal to Tn minus 1. This is the n minus 1 denotes the degrees of freedom and squared into S squared, right? Here actually this n already we have to decide, right? So how this n value you can decide it? So here we put n1. You have to, if we want to estimate sigma, then we have to take the pilot sample, right? So sometimes this sigma you can use as a what will be the for expected value as large as. For the true sigma, what will be the expected to be as large as from the previous theory or from the previous research, we can get sometimes. Otherwise, you have to set the pilot sample, right? Suppose 30 pilot for the pilot studies. Before conducting the actual study, we have to do a small study. Before conducting the actual study, we have to do a small study with a small sample size. That sample size is n, actually 30. N is equal to 30. In some cases, you can take n as, because we have to use very large sample size, 400 or 500 sample size we are going to take for our research. So according to that one, first we are implementing a small study, right? In that we will take n as a 30 or n as a 50. Sometimes we can take that one, right? So based on that pilot study, then we have to estimate sigma. the sample standard deviation. And also if our pilot study sample size, n is the pilot study sample. Otherwise, if we are using the pilot study, right, to estimate the sample standard deviation, then we can use even Z also. Here we can use it, right? If it is estimated by S, then the corresponding Z also you can use, or you can use N as a, this one also valid, N as the sample size for the pilot study, right? You take this degrees of freedom. Then sample size of the pilot study. Right, that also you can use. Otherwise, you can use the critical value Z also. So in some books, both methods are mentioning. You can use also Z also. We can use Z square into S squared over E squared. Right, that's squared into S squared over E squared. The Z you can decide based on the there. To decide the Z value, we don't need the sample size, right? Because only the level of confidence is needed. But if we want to use the T value, then we have to need the sample size. So either you can use the pilot study sample size to decide the critical value, or you can use the Z value with the level of confidence. But this S should be estimated using the pilot sample observations, right? That the formula is this one, or this formulas, whether this formulas also you can use it, right? Now we are coming to the next, determining the sample size for the population proportion, right? So here the margin of error is given by this piece. Margin of error is this piece. Right? So now here also, this P is actually what is sampling proportion. So the sampling proportion should be replaced by the population proportion from the previous, or from the pilot study. Like in the previous one, we can get from the previous studies, or we have to use the pilot study, or sometimes we can take as a conservative value, pi is equal to 0.5. Right? Three methods here we can use to find what is the pi value. Pi from the previous studies you can collect for the current study, or using the pilot study we can find out what is pi, or the conservatively we can take pi is equal to 0.5. So now here also this margin of error, it's in the radical sign. So to find out what is n, then you have to spare this one. By sparing both sides, E squared is equal to Z squared into pi into 1 minus pi over n. So from this we have n is equal to Z squared into pi into 1 minus pi over E squared. Right? This is actually population proportions we are taking as a standard normal sampling distribution. So we have the critical value as Z. This one you can determine from the level of confidence. This pi from the previous studies, or from the pilot study, or by using the conservative value we can take. And E is the margin of error that's decided by the researcher. To what extent we are allowing this estimated value can change. right? So to determine the required sample size for the proportion, you must know the desired level of confidence, 1 minus alpha, which determines the critical value, Z. Right? Then the acceptable sampling error or margin of error that is decided by the researcher. Then the true proportion of success pi. It is actually very difficult to get the pi value, right? So pilot sample, if necessary, pilot sample. If also it's not possible, then conservatively you can decide pi is equal to 0.5. If there is no any information in the given problem, then we can take pi as we are getting, because why here we are taking pi as a 0.5? Here we are our category, these proportions, we are taking a two outcomes only, right? Yes or no, or defective, non-defective, only two categories we are allowing under this one. This is a binomial study, right? Two categories we are allowing. So we assume that both have equal chances to occur. Both has equal chances to occur. But it is very rare situations, right? But anyway, if any information we are not able to get regarding the population proportion, then we have to assume that both categories have equal chance to occur. So 0.5 and 0.5 we are taking, right? So now, how large a sample would be necessary to estimate the true proportion? We want to estimate the true proportion defective in a large population. What is the number of defectives in a true number of defectives in a large population within plus or minus 3% with a 95% confidence. Okay. Here we have assume a pilot sample is P is equal to 0.1. So now Z equals 1 minus alpha is 95%. So we have to decide the Z, 95%, that is 0.95. So alpha is 0.05. From this, alpha by 2 is 0.05. Right? So from the table, so if we plot in the diagram, that value. And this is Z alpha by 2. It is 0.025 and this is also 0.025. Then it is actually 0.475. Right? Then probability of 0 less than Z alpha by 2 is equal to 0.475. So from the Z table, we can say that Z alpha probability of 0 less than Z less than 1.96 is equal to 0.475. From the table, we can identify this as a 1.96. From this, Z alpha by 2 is equal to 1.96. Then we are allowing this from the estimated proportion, it can range from plus or minus 3.3%. So your E is 3%, that is 0.03. Then pi is 12%, estimated P. So you can take pi as, from the pilot study, we say that the sample proportion is 0.012. So this will be considered as our point estimate for the population proportion. So that is 0.12. And by substituting all these figures in this formula, then you can get the end value, right? So here we have for the 95% confidence, Z is 1.96, E is equal to 0.03. So we use this as our estimate pi. Then by substituting this formula, 450.74. So the sample size we have to use to construct a confidence interval to estimate this population proportion, 451 samples we have to select, right? So now almost we are at the end of this confidence interval estimation. So what are the ethical issues we are facing when we are estimating the population parameter? A confidence interval estimate, that is this estimates reflecting the sampling error, right? So, but in the point estimate, that does not reflect the sampling error, but this confidence interval estimate reflects the sampling error, should always be included when reporting the point estimate. So, if you are reporting a point estimate, this interval estimate also we have to support, right? In addition to that one, mainly it's with the research. When you are performing the research and you are, sorry, we are estimating the customer satisfaction, right? We are estimating the level of customer satisfaction. So we are going to use the sample mean as to estimate the level of customer satisfaction. In that case, with the sample mean, we have to also give our interval estimate. So from that interval estimate, we can identify the sampling error. This is in the context of research, right? Then the level of confidence should always be reported to what the level of confidence you used. Whether it is 95% or 99% or 90%. And then what is the sample size we consider? That also we have to report. And the interpretation of confidence interval estimate also you have to report, right? So these four things, when we are dealing with our research studies, these four things we have to consider, okay? Then what are the things so far we learned? We introduced the concept of confidence interval and point estimate. What is the advantages of confidence interval over the point estimate? Then we developed the confidence intervals for the two cases with for the mean. Under the mean, sigma is known and sigma is unknown. And also we create the interval estimates for the proportion. And then we decided how we can determine the sample size for the mean and the proportion settings, and also how we have to use these confidence interval estimations. What are the things we have to report when we are estimating the population parameter, right? So these are the things you will be also evaluated under based on these criteria, right? to apply hypothesis testing procedure to test a mean or proportion. And also you will be able to use confidence interval to perform the hypothesis testing. These three will be explained in the session, but this we are taking as a reference, right? The materials will be uploaded. Using that materials, you have to learn that how we can use confidence interval to perform the hypothesis testing. But these three sections we will learn here, right? Now we are taking a small working place example to get the idea about how we can use this hypothesis testing, where we are going to use this hypothesis testing to solve our problems in the working place, right? There is a manufacturing company. That company is producing cereals, right? That name is Daily Cereals Company. It's producing cereals. So there is in that company, this plant operations manager is responsible for monitoring the amount in each cereal box filled, right? They are using the machines to fill the cereal boxes. So each and every day, the operation manager has to monitor what is the amount in each and cereal box is filled, right? But in the standard of the company, the mean weight of the per box should be 368 grams, right? Each and every box must consist of 368 grams per box. So if the filling process is not fill accurate weight, then this is the operations manager responsibility to adjust the process. If the filling weight is differ from 368 grams, then the operation manager has to adjust the filling process, filling machines, right? So how he can check whether the process is happening perfectly? So for each and every packet, it is very difficult to measuring each and every packet because it's a large scale production. So per day, they are producing, say that they are producing 5,000 boxes per day. They are producing. So is it possible to to weigh each and every box? No, it's time consuming, and also the operation manager has to every day he has to measure it, and it's also very difficult because it's take a 5,000 box, then every day it's very impossible to measure each and every box in the 5,000 lot, right? So how he can resolve this problem to check whether the mean weight is 368 of 5,000 boxes in each and every day. So how he is going to do? He is selecting a random sample from the 5,000 lot. He is selecting a random sample of 25 boxes and taking measure of these 25 boxes. And by looking at those 25 observations, now he is going to decide whether the machine is working properly or not. If the machine is working properly, the weight should be how he can decide this machine is working properly based on this 25 cereal boxes, right? So now this begins with our hypothesis testing process, right? So now a sample mean. So from these 25 selected boxes, we can calculate to validate a claim that the population mean weight is 368 grams. Now he has to prove that because if the filling process is properly worked, the population mean weight should be 368 grams. So now we have to validate the population mean weight is 368 using the 25 mean values. 25 values of the boxes selected. From that 25 boxes value, we can calculate the sample mean. By using that sample mean, we can validate this statement, right? So the process of validating a claim about the parameter, right? The claim should be regarding the parameter, but the parameter is unknown. But from the previous knowledge, we have making a claim about the parameter. So in the given example, the parameter is population mean, that is 368. Based on the statistic calculated from the randomly selected sample. In the given example, our statistic is sample mean, right? This is the general statement, right? But with our example, the parameter is population mean and the statistic is sample mean. So is called the hypothesis testing. So generally how we are saying that the process of validating a claim about the parameter based on the statistic calculated from the randomly selected sample is called the hypothesis testing. Now we have to prove that the claim or statement made about the population parameter is true or false. This validation should be based on the sample statistic, right? So hypothesis testing would allow to infer mean to make decision or concluding either one of the following in the daily serial scenario. The above example, we can make either one of the decision under the hypothesis testing, right? The population mean of the mean of the population of cereal boxes is 368 grams, or the mean of the population of cereal box is not equal to 368 grams. Either one of the decision we can make under this hypothesis testing process. So that means when we are validating a claim about the population mean in the previous given example, either we can make the decision that the population mean is 368, or we can make the decision the population mean of the cereal box is not 368. If we make the decision the mean is 368, then the filling process is working properly. If we make the decision this population mean is not 368, then the filling process is not working properly, and then this filling machine should be adjusted, right? To make the exact filling, right? So, but these both decisions have based on the sample we selected from the 25 boxes of the cereal from the large production run, right? Right. Now, what is a hypothesis? Right? So, hypothesis is simply we can say that is a claim or assertion or statement. Claim or assertion or statement about a particular parameter of a population. About a particular parameter. Now, we are making a statement about a parameter of the population. This parameter may be population mean or population proportion. In your case, or population standard deviation. But here we are only considering the mean and proportion. So, whatever statement we are making about a population parameter, that is called as a hypothesis. So, what is simply you can say that hypothesis is a claim or assertion about a particular parameter of a population proportion. Example, based on the previous weight, mean weight of daily cereals is 368 grams per box. That is per. Now we are looking at our milk powder boxes. They specify the mean weight of this boxes. The weight of this boxes, net weight of this box is 468 grams or 450 grams. Right? So that is mu. In this case, mu is equal to 368, because why here we are using the notation mu? We are looking at the mean weight. So mu is equal to 368. Then the next statement, the proportion of adults in a particular city with cell phones, right? The proportion of adults in a particular city with cell phones is 0.68. That is, pi is equal to, because we are looking at the proportion. So pi is equal to 0.68. So that means 68% of the adults in a particular city having cell phones. Okay? So these two are the examples of the hypothesis. This hypothesis is related to the population mean, and this statement is related to population proportion. So we are naming this as a hypothesis. Okay? Then when in the hypothesis, when we are formulating a hypothesis, there are two hypotheses we have to formulate. One is called a null hypothesis, that is denoted by H naught. Right? So the null hypothesis denoted by H naught represents the current belief about the population parameter in a situation. In the previous example, the current belief is mean weight of a cereal box is 368 grams. Right? So that is mu is equal to 368. Now, actually, they want to test the filling process of daily cereal company is working properly. If it's working properly, what? This is a normal statement, but we have to prove this statement, we have to convert this statement in a statistical terms. So in statistical terms, we have to say that if it's working properly, the mean weight of a cereal box should be 368. So that is H naught colon, how we are specifying that H naught, mu is equal to 368. Right? So null hypothesis always reflects the current belief about the population parameter. Right? So always don't forget, the hypothesis is always related to population parameter, not about the sample statistics. If we are specifying H naught, X bar is 365, that is wrong. Hypothesis, either it is null or alternative, hypothesis should be related to the population parameter, not a sample statistic. This is very important, right? And also, the statement of null hypothesis is always contains an equal sign. When we are reflecting our null hypothesis is in a statistical term, there should be, the sign should be equal sign. Right? What is the exact value of the population parameter? That should be specified under the null hypothesis. So this is the main characteristics of null hypothesis. This has equal sign. Mu is equal to 368. If mu not equal to 368, we can't specify as this null hypothesis. Right? The null hypothesis always should be contain equal sign that represents the current belief about the population parameter in a situation. Right? But based on sample results, if the null hypothesis is rejected, that means we decide that this statement is false. Based on the sample size, we decide that because under the hypothesis testing, two decisions we can make. One, our statement situation is true or the situation is false. If this situation is false, true, then okay. We say that it is 368. But based on the sample size, we say that it's false. Then what is your decision? That decision should be specified in the alternative hypothesis. Right? So whenever a null hypothesis is specified, an alternative hypothesis is also specified. And it must be true if the null hypothesis is false. If the null hypothesis is false, then it must be true. Right? So alternative hypothesis is denoted by H1. That is opposite of the null hypothesis is H naught. Right? Suppose if H naught, we say mu is equal to 368, then the opposite is mu not equal to 368. That is specified as our alternative hypothesis. Right? So it represents a claim about the parameter that is expected to prove. Null hypothesis is the current belief of the situation. An alternative, we are expected to prove it. And now we say that we have a doubt. The process is not working properly. In filling, the filling process is not working properly. So if it's not working properly, what is meaning? The mu not equal to 368. That is specified in the alternative hypothesis. So in the alternative hypothesis, it never contains an equal sign because we already say that the null hypothesis have equal sign. So that an alternative is opposite to the null hypothesis. So it has never contained equal sign. So there are three options we can specify in the alternative hypothesis. It can contain not equal sign, or greater than sign, or less than sign. Now we say that the filling process is improved. In this it's not possible. The waiting time, right? The waiting time is improved by the system. The waiting time is improved. So now here, suppose if the waiting time to receive a service, the waiting time to receive a service in a banking counter is now currently it is at 9.5 minutes. The waiting time to receive a service in a counter is 9.5 minutes. Now we say that the system is improved. So now our null hypothesis is mu is equal to 9.5. And our alternative, we are expecting the system improves the waiting time. So mu less than 9.5. If the system is improved, the waiting time should be lesser. So it is less than 9.5. So now here we use in our alternative hypothesis mu less than sign. So now we believe that our filling process is not working. The filling process is overweight, overfilling. The weight of the filling process mu is equal to 368, and it believed that the weight is over. The filling weight is over, right? So mu greater than 368. Right? So similarly, according to our given scenario, we can decide what is the appropriate sign we have to use in the alternative hypothesis, whether not equal sign, because in writing your null hypothesis is not problem, because we say that it always has equal sign. Right? But what is the sign will be in the null alternative hypothesis? There are three possibilities: not equal sign, greater than sign or less than sign. What will be the appropriate sign? So that you have to decide based on the given scenario. So what the thing we want to prove, according to that, the signs will be decided whether it is a not equal sign or greater than sign or less than sign. Now, there are three scenarios here we have, right? So under these scenarios, we want to form null and alternative hypothesis for the following claims, right? So now we will go one by one. First, state the null and alternative hypothesis for the following claims. The first claim is the average waiting time for the customers of Smart Supermarket at the checkouts greater than 15 minutes. Right. So now, here first you have to identify what is the parameter related in this statement. So here, average waiting time. Always it is a time, it is a measurable, then the appropriate parameter is mean. So the parameter is mean. Then what we want to prove, right? Whether it's greater than 15 minutes. We want to prove the waiting time is greater than 15 minutes. Okay? According to that, now we want to decide, write the hypothesis. So now we identify mu. Parameter is a population mean. So we are define mu is mean waiting time for the customers. We define mu as a mean waiting time for the customers of supermarket. From the given scenario, you can identify the description, right? Mean waiting time for the customers of supermarket checkouts then our null hypothesis, H naught. What is H naught? Here, we want to find out whether the mean waiting time is greater than 15 minutes. So, but in our null hypothesis, always we have a equal sign. So, don't forget that principle, right? To form the null hypothesis, it has always have equal sign. So, we assume that the current mean waiting time is 15. We assume that the current mean waiting time at the supermarket is 15. Then H1 is opposite to that one and also not has equal sign. So there are three possibilities. You can use not equal sign, or you can use greater than sign, or you can use less than sign. But here we want to prove that the mean waiting time is greater than 15 minutes. So now our null alternative hypothesis H1, that is mu greater than 50. Now you say simply how? It is a very simple, right? This is already we learned that null hypothesis must have equal sign, right? This is our alternative is opposite to the null hypothesis. So there are three possibilities to specify. It's not equal sign, greater than sign, less than sign. To decide, you look at the scenario. Right? So now here that is, and also the alternative hypothesis, what is the statement we want to prove? Now we want to prove that the waiting time is greater than 15 minutes. So mu is the waiting time, mu greater than 50. Right? Now here we are coming to the second exercise. Whether the waiting time to place an order in a fast food restaurant has changed in the past month from its previous population mean of 4.5 minutes. So here also, first decide in this statement. Here we want to prove that statement whether the waiting time is changed from the previous month. The waiting time to place an order in the fast food restaurant changed from the previous month. But in the previous month, the waiting time is 4.5 minutes for a customer. So here what is the parameter related to? The parameter is population mean. It is a waiting time. So the waiting time usually we can measure with the mean value. Right? So now first you define what is mu. Mu is mean waiting time to place an order in a fast food restaurant. Right? Then H naught. What is the actual current situation? From the previous population mean value of 4.5. Now they want to prove that whether it's changed. So for the alternative, there are three possibilities: not equal, greater than, or less than. To decide this one of the sign, you have to look at the statement. So whether the waiting time to place an order in a fast food restaurant has changed. So we don't know whether it's increased or decreased. One of things will happen. It may increase or it may decrease, but we don't have any solid idea. Only with the idea, we want to check whether it's changed or not. So mu not equal to 4.5. Only this sign only we can use that, because either it's greater than or less than, there is no any indicator. It's a increased or decreased. There is no any indication. Only whether changed. So it may increase or it may decrease, but we don't know the direction. So we specify not equal to 45. Right? Now here one thing you look at in the previous slide. Here mu is equal to 15. So actually, in some books, if there is only greater than sign in the alternative, in some books, this H naught is specified. Mu, because H naught and H1 are opposite. Right? So mu, if mu greater than 50, then mu less than or equal to 50. This is also possible. In some books, they are stating the null hypothesis in such manner. If we have the directional hypothesis, the directional hypothesis means the alternative should have greater than sign or less than sign. Right? If the alternative should have greater than or less than sign, then when the null hypothesis with the equal sign, the other part also will have. Right? If you have a greater than sign, then you can write this one as a 15, but this is also okay. Right? So for your convenience, you can just keep as a equal sign. Right? But when you are referring some books, this possibility also you can get it, but there must be this equal sign also must be there. So there are two options, less than or 15. 15 and less than are possible under H naught. Right? Here you don't know problem because greater than, less than, equal, so not equal to, both are same, opposite directions, right? And third example, whether the new process developed in a fast food chain to ensure that the orders at the drive-through are filled, correctly, improves the previous process filled orders correctly 85% of the time. Right? So here the filling process in the drive-through, customers information filling, right? So they are filling whether the filling process is, they want to check whether the filling process improved than the previous one. They want to check whether the filling orders, filling orders process improved or not. So now it's related to the proportion. This statement is related to proportion. Whether if we are taking the 100 orders, then whether 85% orders should be correct filled or not. Right? So now we define pi. It's related to the population parameter is related to proportion. So we are taking proportion pi. That define percentage of orders or proportion of orders, right? It is we are taking the proportion of the orders. Proportion of the orders. Proportion of the orders filled correctly at the drive-through. Proportion of the orders filled correctly at the drive-through. Proportion of the orders filled correctly at the drive-through. So H naught is now related to pi. We know that that's also equal sign. From the previous process, they said that it is 85% of the time the orders are correctly filled. So 0.85. Right? Proportion. If it's a percentage, then we can say that it is 85%. Now we are looking at in the proportion, so 0.5. Then for define the alternative hypothesis, we can use not equal sign or greater than sign or less than sign. So now we have to decide, right? So whether the new process developed, now here they are developing the new process to ensure that the orders at the drive-through are filled correctly improves. The term improving. Now they developed a new process in terms of improving the previous process proportion. So currently it is a 85%. Now they developed a process for improving the orders correctly, to filling the orders correctly. And now they want to test whether it improves. So if it's improving, this percentage should be more than this one. The filling order proportions correctly is more than 0.85. So H1, in this case, we are selecting. If the process should be improved, the orders here, we are looking at the correct orders. So the filling the purchase percentage of the correct orders also should be improved. Then pi greater than 0.85. Right? So in some books, so if it's only here greater than sign we have, so this also possible. H naught in some books they write as a pi less than or equal to 0.85. So after deciding your H1 sign, then you can specify what the sign will be into H naught. Right? So now this is a method of formulating our hypothesis. Right? Now we learn how we can formulate the alternative and null hypothesis based on the population mean and based on the population proportion. So for the first step in the hypothesis testing is deciding your null and alternative. So to decide how we have to formulate null and alternative hypothesis, first we have to identify whether it's the hypotheses are related to the population mean or population proportion. If it's the population mean, then it's the sign will be related to mu. And if it's the population proportion, then the sign will be related to pi. So first you decide the sign parameter, it's mu or pi, and then also define what is mu in the case and what is pi in the case related to your problem. After defining your notation, then you can use H0 and H1 in such manner, right? Now we are coming for the hypothesis testing process. So now we want to decide, we are looking at the employees. They are working in a particular company, right? Employees in a company. And the company believes that the average age of the employees is 50 years, right? It is a very old, large company. And there are employees are working. And they believe that the company's employee average age is 50. So now the current belief of the company is, because we are talking about the population parameter mean, so mu is equal to 50. Now we have to decide whether this is true or false. Right? So what we are doing, very large number of employees are there. So we can consider, we are not able to consider in each and every employee. So now we are selecting a random sample of employees from this population. So that is consists of few members, right? Then from these selected members, we are asking their age. And we find out that this sample mean is 20. The average mean weight of 20 of the sample is 20 years. Now we have to decide, based on this information, now we have to decide whether mu is 50 or not. So if from this information, the mu is not possible. Now we got x bar is 20. Now you look at how the difference. We believe that mu is 50, but we got x bar is as 20. So it is unbelievable, right? There is a huge difference. But we can't say that using this, just by comparing these values, we can't say that whether it's likely or not likely. So now based on this one, we have to decide whether mu is equal to 50 is likely or not likely. Is x bar is 20 likely if mu is equal to 50? If mu is equal to 50, whether x bar is equal to 20 likely. So if x bar is 20 is not likely, then it is false information and H0 should be rejected, right? X bar is equal to 20 is not likely from this population, of average age 50, then this is false information and this should be rejected. So how we can decide whether this 20 is likely or not likely? That process is hypothesis testing, right? So for that, what are the likely values for 20 to say that mu is equal to 50? Now we have to find out what are the likely values for X bar to say the average age of the employee is 50. So we are taking the sampling distribution of X bar, right? For the sampling distribution, the mu is equal to 50. And now it is 20. Right? So if the 20 is unlikely, right, then we have to reject the null hypothesis that mu is equal to 50. If we decide 20 is unlikely, when mu is equal to 20, if mu is equal to 50, right, and from this population, X bar is equal to 20 is unlikely, then H naught should be rejected. So what are the possible unlikely values? Now we have to find the cutoff, right? If from this cutoff less than 20, these are the unlikely values. From the cutoff particular value, if less than the particular value, then it's unlikely values from this sample. And also if the particular value is greater than the particular value, that mean value is also unlikely. So now we have to decide at the cutoff values. Beyond those values are listed unlikely values. We have to decide. Now we are deciding our cutoff for the Z score, right? For the BBA, if your Z score is greater than or something, then you are possible to get the BBA degree program in a particular university, right? Likely, here also we have to decide the cutoff values for the sample mean. For what are the sample means we can get then when the mu is equal to 50? When the mu is equal to 50, what are the possible likely values for the sample mean? Right? So that's we are going to decide. So to define the unlikely values of the sample statistic, when the null hypothesis is true, we have to define the unlikely values of the sample statistics. That is the first step. Define the unlikely values of the sample statistic if the null hypothesis is true. So these unlikely values defines the rejection region of the sampling distribution. Right? These unlikely values decides the rejection region of the sampling distribution. This rejection region is denoted by alpha, that is called level of significance. This rejection region is defined by the alpha, that is level of significance. Then this level of significance are 0.01. Possible, usually we are taking 0.05 or 0.10. This level of significance is selected by the researcher at the beginning. And it's providing the critical values of the test. So mainly this level of significance is the rejection. It defines the rejection region, and it was decided by the researcher at the beginning of test and also used to decide the critical value. That means this is the critical value is the border point. Beyond these values are the unlikely values. Beyond that region is the likely values. Now suppose for example, we are saying that H naught, our filling process, right? H naught mu is equal to 368. Now we want to decide H1. We want to prove the filling process is not working properly. So if it's not working properly, then mu not equal to 368. Then we use our sample distribution X bar. And here, this is our H naught, because this is a population mean value. So mu is equal to 368. Now we want to test. We say that our level of significance, alpha, is 0.05. Right? So now this alpha here not equal sign, because so this alpha should be allocated for the two tails. It is alpha by 2, that is 0.025. And this is also alpha by 2 equal 0.025. Then this value is, as in the confidence interval calculation, Z alpha by 2, and this is Z minus Z alpha by 2. When it's 0.025, actually it is 1.96. According to the standard normal table, it is 1.96 and it is minus 1.96. So if the, now it's actually Z we are taking, right? Because we are using the notation Z. Otherwise, we take it is a X1 bar. As it is X bar, don't take this one, right? X1 bar, it is X2 bar. Right? Then, according to this one, we can find out from the value X1 bar using the standard normal with this alpha by 2 area. We can get X1 bar. If the X1 bar larger than this values, if your mean values are larger than X1 bar, right? If your mean values are larger than this particular X1 bar value, then your mu is equal to 368 is false. And also either if the mean values are less than X bar 2, in that case also, we cannot get mu is equal to 368. The mean value is false. Right? So, based on this X1 bar and this X2 bar are decided based on this level of significance. Based on this level of significance. And with mu is equal to 368, based on the level of mu and alpha, we can decide the X1 bar and X2 bar. Right? And then by comparing these X1 and X2 bar is our sample results. Your sample mean value is greater than or less than X1 and X2 bar, then mu will be rejected. That means we have the population mean not equal to 68. So if your mean value is fall in between this X1 bar and X2 bar, then there is a possible of getting the sample from this mu is equal to 360. This value is called a critical value, and this critical value is depending on your H naught value and this level of significance. Right? So this is called as a rejection region. Right? This is called as the rejection region. This both tails as called rejection region. Rejection region for H naught, right? Rejection region for H naught. So the sample mean values beyond these boundary values, then there is this mean value is unlikely, right? And so your H naught should not be, the mu should not be 368. If your mean value is within this range, then this is a non-rejection region. So there is a sample is possible from the population which has the mean value 368, right? So now we are looking at level of significance, how the level of significance and the rejection region, right? So it is, now we are looking at, this is very important to identify our rejections regions. That's rejections regions are deciding based on the alternative hypothesis. Now, for example, our null hypothesis mu is equal to 3 and alternative mu not equal to 3. So if your alternative hypothesis have not equal sign, then that test is called two-tail test. If the alternative hypothesis has not equal sign, then the test is called two-tail test. So there, the level of significance is set alpha, and it will be shared for the two regions, right? So two tails will be the rejection region, alpha by 2 and alpha by 2. This value, the yellow star, right, point indicate the critical value. That point is the border point. This is the extreme point for rejecting the region. Beyond this point, your H naught will be rejected, right? That means there is no possible for getting the sample from that population. So H naught will be rejected. So this called as a critical values, and the rejection region is shaded. These are the rejection regions of H naught, and these are the non-rejection regions. If mu greater than 0, then that is called the one-tail test. If the alternative hypothesis has greater than or less than sign, then that is called a one-tail test. In the one-tail, there are two tests, upper tail test or right tail test, then lower tail test or left tail test. Right? So if mu greater than sign, if the sign is greater than in the alternative hypothesis, that is called the upper tail test, then you have to consider right tail of the diagram, right? So the level of significance alpha marked here in the right tail. This is a rejection region, right? And if alternative hypothesis has less than sign, then that is the left tail will be marked, right? And this region, probability of this region is alpha, that is lower tail, right? So to decide whether it's a two-tail test or one-tail test, you have to look at the alternative hypothesis. In the alternative hypothesis, if H1 has not equal sign, then two-tail test. Then the level of significance. Right? Then there is a, if not equal sign is there, then it is a two-tailed test. Right? So if greater than sign or less than sign is there in the alternative, then that is a one-tailed test. Right? So in the one-tailed test, there are two cases. It may be upper tail test or lower tail test. For the upper tail test, greater than, then you have to mark the right tail. So upper tail also, look at the right, referred to as right tail test. So in the right hand side of the diagram will be marked, and that is alpha. Here alpha by 2, if the level of significance is alpha, for the two tail, that will be divided alpha by 2, alpha by 2. But for the right tail test, the level of significance alpha is marked in the left or right tail. That is depending on greater than or less than sign. And these regions are the rejected regions. Unshaded regions are called non-rejection region for H node. Right? This is rejection region for H node. Then, what are the errors we are making in the hypothesis testing? Here also, because we are depending on our sample results to make the decisions, we are depending on the sample results. If our sample selection went wrong, right? If our sample selections went wrong, then there is a possibility of making errors. Right? So those errors, there are two types of errors we can make. One is called as a type 1 error and other one is called as a type 2 error. Right? So what is type 1 error? When a true null hypothesis rejected, our null hypothesis is actually true. Indeed, that is true. But based on our sample, it's rejected. So that is a type 1 error. And rejecting a true null hypothesis is considered as a serious type of error because actual situation is rejected based on our sample. So that is a very serious type of error. So for that purpose, we have to take our sample properly. So in your third year research methodology and stats also, you further learn if the sample selection is perfectly appropriate. If you are selecting a sample in a wrong manner, then this kind of situation errors, right? And you make your decision in the wrong decision you have to make in the population. So that's why this will affect your business also. If you are making the wrong decisions, all these hypotheses are related to our business scenario. And if we make wrong decision because of our sample, then you get loss in your business. So the sample selection is very important. And rejecting a true null hypothesis is and wrongs to make a wrong decision related to business. Rejecting a true null hypothesis leading to a wrong decision in your business. Right. Then, so here we are taking the probability of rejecting type 1 error is taking as a alpha. So here we are, because the sample variability, this is occurred due to the sample's variability, because sample to sample, our results will differ. So to accommodate this sample variability, we are taking the probability of type 1 error as a alpha, that is called level of significance of the test. So the level of significance of the test is probability of type 1 error. The level of significance of the test is indicating the probability of type 1 error. What is the probability of type 1 error? Is the probability of rejecting a true null hypothesis, right? Alpha is probability of rejecting type 1 error. Probability of rejecting the true null hypothesis. Right? 1 minute. Right. So by using this, because our hypothesis testing is depending on the level of significance. The level of significance is the probability of type 1 error. But what is type 1 error? Rejecting a true null hypothesis. Probability of rejecting a true null hypothesis is level of significance. This is said by the researcher. Then type 2 error, opposite to type 1 error, fail to reject a false null hypothesis. Right? The sample is not enough or not provide the results to reject. Actually, the null hypothesis is false, but it's failed to reject. So now we say that our null hypothesis is true. Based on our sample results, we deciding the null hypothesis is true. However, actually it's false. So fail to reject a false null hypothesis. So the probability of type 2 error is called, denoted by beta, that is the power of the test. Right? This is related to power of the test. But we will not look at this power of the test here. This power of the test we will learn in the third year statistics subject. In the third year statistics subject, with the statistical softwares, we will learn third year statistics. In that, we will learn about the type 2 error and the power of the test. Here, important, the type 1 error. Anyway, you have to know what is the difference between the type 1 and type 2 error, what is the level of significance, and what is the type 2 error probability. These are the things we have to know that, right? Right. So now here we have summary. Based on this table, what are the decisions, what are the errors we are getting in the hypothesis testing, right? So outcomes and probabilities of hypothesis testing, the actual situation. H naught is true and H naught is false. This is our situation. But the decision here, there are two decisions. Do not reject H naught and reject H naught. Right? Based on our sample, either one of the decision can occur. Do not reject H naught, not reject or reject H naught. Right. Then now we intersect with the actual decision and the decision. right? If the decision is reject H naught, but actual our decision is not reject H naught. Actual situation H naught is true. So there is no error, right? If this happens in our hypothesis testing, that is no error. So the probability of getting no error is 1 minus alpha. Right? Then based on our sample, the decision is not reject, but the actual situation H naught is false. So when H naught is false, based on the sample, our H naught is not rejected. So that is type 2 error. Then the probability of getting type 2 error, that is denoted by beta, right? These are the probabilities, right? These are the probabilities, and these are the decisions and the actual, right? Then if our decision is H naught, rejecting H naught, but our actual situation is H naught is true. H naught is true, that is rejected. That is called as a type 1 error. And the probability of getting type 1 error is denoted by alpha. Right? Actual situation, H naught is false. But based on the sample, H naught is rejected. It's false, it's rejected. Then there is no error. Then the probability is 1 minus beta. So these are, if this is our decision, H naught is not rejected and H naught is true, no error. Similarly, H naught is rejected. When H naught is false, no error. Right? But when H naught is false, it's rejected, then type 2 error will occur. That is denoted by, the probability is beta. When H naught is true, it's rejected, then type 1 error will occur. That is denoted by alpha, level of significance. Right? So this you have to understand outcomes and what are the outcomes of the hypothesis decision and what are the actual situation. And according to that, when two decisions occur, there is no errors. When two decisions are occur, other two decisions are occurred, type 1 error may occur or type 2 error may occur. Then tomorrow I will stop these lectures today. Then Monday morning, 6:30 to 8:30, we will meet again to understand the hypothesis testing, and we will do some examples and this hypothesis testing procedures, and then we will do the applications, right? So what about Monday morning, 6:30, are you okay? Class rep?
Yes, ma'am.
Okay, so Monday morning, most of the students, you don't need to experience the power cut, right? So Monday morning, 6:30 to 8:30, we can have the lectures, right? So before coming to the Monday morning class, please study these sections very clearly, right? Then if you have any doubt, you can ask, you can clarify your doubts after the session or before starting the session, right? And then we can, because to continue rest of the section, we need a clear understanding about our hypothesis testing. Mainly the decision of the hypothesis testing, the critical value, the level of significance, the null hypothesis, the alternative hypothesis, then deciding the critical regions, right? These are the things very important. So before the by reading the previous slides, you can get the understanding, and also the two materials were uploaded, right, regarding the hypothesis testing population mean and the population proportion. So first you read the population mean procedure. In that population mean reading material, the starting sessions are there, right? So you can get the understanding by reading those both materials, my lectures materials and the reference material, you can get the clear understanding. So before coming to the session, please refer to my material and the reading material uploaded to get the clear understanding. Then only you can get the proper understanding. The sessions we are going to study on the next Monday, right? So anything you want to ask from me? And also under the section practice questions and the continuous assessment, two practice exercises were uploaded for the chapter 1, 2, 3, right? So practice those questions before your continuous assessment exam 1, right? And also, now we have to decide when you will have to have your assessments exams, during 6:30 to 8:30 or after that session. So based on that one, I will decide the time slot for your continuous assessment. If we have the exams during morning 6:30 to 8:30, then there is no internet problems, right? And also there is no power problems. So what about your decision? So the class rep, you are the responsible person to decide your times, whether we want to have morning time or the time slot you have to decide, then the day and date I will decide, right? So for 3 exams I will have, so for these 3 time exam, the time slots is important. So if the time slot you have to give and the day I will decide during 6:30 to 8:30 time or not. So the class rep, today you have to inform that one. After you have to get from all the students' opinion to have the exams during the morning 6:30 to 8:30, right? Otherwise, then the daytime will have that you have to decide, right? So you decide, and today by evening you have to tell me, right? Whether morning time or during the daytime you will have morning or after 8:30. That you have to decide. Then the date I will inform, right? So now I end the meeting, and Monday morning 6:30 we will meet again, right?